So the purpose of today's class is to talk about neural networks, at least get us an introduction into neural networks and to get started with a little bit of machine learning so that we can use this to model different types of problems. So the first thing that we want to talk about, or at least sort of define what a neural network is to talk about machine learning algorithms. So machine learning, and let me increase the size on this. Classification algorithms. What you're trying to do with those is basically find curves that separate our data. Separate our data. That's the idea behind it. Sometimes our dimensionality is too large to visualize. I'm going to say instead of sometimes, most of the time it is, because if you're above 2 or 3 dimensions, then you can't really visualize it. Too large to visual. All right, and let me make this big. So that's the idea of a neural net, or at least what we're trying to do is find this curve. And so how we're going to start this thing out is we're going to begin with a simple line, and then we're going to go to maybe a more advanced line. In other words, one that has a y-intercept, and then we're going to go into curves, right? So that's the curve that I'm talking about at the beginning. So a neural network is an example of a machine learning algorithm that uses data to, and I'll put this in quotation marks, to train network of weights in order to classify new data. So that's what we're going to try to do today. Classify new data. This one large or longer as well. And so those are the two big things that we want to be able to do. All right, so let's start off with an example. So of course this is going to be as easy example as I can think of. So very simple example is one where I would like to use data. So I'm going to have one piece of data to train our network on. And what is the simple example going to do? Well, we're going to build a model that does something very simple, that converts kilograms to pounds. And we're going to start off, so our model is really the weights that are contained inside the model. That's the only thing that's going to persist from one generation to, or one piece of data to the next. So our model right now, we're going to arbitrarily just let our W, I could call this 1, but I'm going to call it 1, 1 because it's going from input to final nodes. We're going to let that be 0.5. Again, very arbitrary. And we're going to use one piece of data that we know. I know 100 kilograms is equal to 220.5 pounds. So I know that, and I'm going to use that in order to make our model. We're going to use this one data point to train our model. And then we can look at, once we have it trained, and it's only going to take one piece of data for this particular one, because it is a simple example, then we can use this model in order to predict or classify others or give the number of pounds for a particular X value. So our X in this case, our input, is going to be 100. And And we're going to let that go into our first node. Call that node 1. And this is my input layer. And I'm only trying, at this particular stage, I'm only trying to get you used to the nomenclature of what things are called in this neural net. And we're going to let this be W11. That's going to be 0.5. And this is going to be our final layer. Sometimes you'll see this called an output layer. I'm not going to call it that. I'm going to call it final, just because I'm going to have outputs later on. So, matter of fact, I'm going to have an output right now. So my output for this one, if 100 goes in and my weight is 0.5, then 50, because all you're doing is multiplying your x times your w, and you get 50 as your output. So this would be O1 is equal to x1 times w11. Now let me write that the other way around. W11 times x1. And I'll go ahead and put a 50 in purple here. And the problem is it's not equal to. So currently this is not equal to 220.5 pounds. So our model is currently not correct. But what I would like to do is I would like to use this thing called error in order to make that work. So I'm going to define this thing E1, and that's just simply going to be, I forgot to put this in blue, so this will be our x1. This target is going to be y1. So this is our x1. It's going in. Output is purple here. It's just equal to that. And the green piece is going to be is my 220.5. So currently E1 is equal to Y1 minus O1, where Y1 represents the target, O1 represents the output from the model, and currently we have E1 is equal to, let's see, Y1 is 220, so 220.5 minus the output, which is 50. And so we know we have issues here with this one because it's sitting at 1. So the error is 170.5. And we want to use this to fix our model. And what do I mean by our model? Again, our model is our weights. So we need to use that error in order to fix this 0.5. So W11 is obviously not 0.5. And so let's figure out how to do that. So the question really is, how do we adjust the weight based off the error? How do we adjust the weight? In this case, it's just one weight, but in general, it's going to be lots of weights based off the error. And so we'll just let W11, so we'll say W1 is our W11. We'll say W11 is our old weights, and then W11, our new weight, is going to be simply W11 old is equal to 0.5, so plus some delta W11. And we don't know what that delta is yet, but that's sort of what we're going after. And we want, basically what you want to do is you want to minimize your error. So we would like to minimize the distance from y1 to O1 new by adjusting delta W11, because we know delta, we can't adjust W11 old. It is what it is. It was 0.5. But what we can do is adjust W11 new, so I can put this W11 new. So I want to, basically what we're trying to do is find out what that guy right there is. So let's let Y1 minus O1, I'm going to call it old, O1 old, and that's going to equal to our current error. And then Y1 minus O1 new, hopefully, is equal to 0. That's what we want it to be equal to. So therefore, Y1 must be equal to O1 new. Now, this is a lot of sub ones and a lot of nomenclature here, all to get us to this little piece right here, so that I can just take this and substitute it back in here for Y1. So lots of ways to write this thing, but so I want O1 new minus O1 old to equal to our error. So what is O1 new? How would I get that? It would be our new W, so it would be W11 new times X1 minus W11 old times X1 is equal to my error. And we just said that W11 new is equal to this piece, so we can simply substitute that back in. So W11 old times X1, let me take that off, plus delta W11 X1 minus W11 old times X1 is equal to my error. And then just distribute this, and you get this one minus that is equal to E1. And then if we go delta W11 X1 is equal to E1, then in order to solve for what delta, so delta W11 is equal to whatever your error is divided by your X value. So this becomes the sort of the formula that we're looking for in order to update our weight for this particular problem. So, well, for this type of problem. For this particular problem, it would be, so our W11 old is equal to 0.5, and delta W11 would equal to my error, which was 170.5. We get up there in red, divided by whatever X1 was, which would be 100. And so that would equal to, let's see, move over your decimal place 2 places and you get 1.705. So my W11 new, which is, you know, what we're trying to do, trying to find the new weights, is equal to my old weight, 0.5, plus my delta W11, which we just solved for, and it should be equal to 2.205. So now if you took my model, so my model now, my new model, if you want to call it that, is just whatever your new weight is. So W11 is equal to 2.205, and it should work for, so this one should work for all of your data that you have. For example, if you took 100 and multiplied it by 2.205, you're going to get 220.5, which is exactly our data point, 100, 220.5. And we're going to have exactly 0 error. Okay, so that's the first part. How do we use data in order to update our weights? That's a way of doing it. So really the next question is, why do we learn incrementally? Why do we learn incrementally? So we're going to give in order to understand this, we're going to give another simple example. And our simple example is going to be, we want to classify. So we're going to collect data, we're going to classify a bug as either a ladybug or a caterpillar based on their length and their width. So if I had this, then if I had to collect some data on this, it might look something like this. And we're going to do this in 2 different ways. So the first way is to simply have one input, and then in a few minutes we're going to come back and we're going to put it into the neural net version of it, and we're going to have 2 inputs with the classification. So for this first piece, I'm just going to let my length be my x and my width be the y. And what I want to do is I want to figure out, can we classify? So classification based on a model. So the input right now is going to be, let's say 3. If I had a bug and it was 3 long by 1 width, that would probably be a caterpillar. And if I had one that was the other way around, 1, 3, that would probably be a ladybug. And the question is, can we create some sort of model that, I don't know, maybe looked at something at 2.5, 0.8. So this is my new data. So this might be the new data. And I want to use a model to say, okay, is this a caterpillar or ladybug? So that's the question. So what would that look like? Well, we might want to sort of draw this thing, and our dimensionality is not getting in the way yet. So 1, 2, 3, 1, 2, 3. And we'll let my model look something like this, where y is equal, tell you what, let's let it be O is equal to WX. And that's an O, not a 0. Wouldn't make any sense for it to be 0. So if that's the case, then I can put, let's see, let me draw the caterpillar in green, and the caterpillar would be at 3, 1. So I'm maybe located there. And let's let the ladybug be in purple, and it would be there. And the new data that I'm looking for, maybe it's at 2.5.8. So maybe it's sitting right here. So the question is, how would you classify this one? And you would, I mean, if you're just looking at this picture, you'd probably classify it as a caterpillar because of the way it's it's closer to a caterpillar than it is a ladybug. But the question is, well, how do we make that happen? How do we make that with just using data? And I claim it's a lot like what we did up here, right? So let's get the formula for delta W, or delta W was equal to what? Y minus O divided by, because that was my error, divided by x. And you can put the sub i's on there, sub I. When we have more than one piece of data. Before we only had one piece of data, but you might have more. Matter of fact, we are going to have more pieces of data for this problem. So delta, let me just write that somewhere down here so I can remember what it looks like. So delta wi is equal to y sub I minus o sub I over x sub I. Okay, so let's start using our data, and we have to have a starting point. So let's arbitrarily say that W starts off at 0.25. Now that's a really bad classifier. If I'm going to draw that one on here, it would be probably down here somewhere. But what we want, so this is 0.25 times x. But we want to use this data in order to make the 0.25 times x better. So let's learn 3, 1. And what would I do then? So O1 would equal 0.25 times 3, so that's 0.75. And then we get, now we need to find what delta W1 would be, and that would be Y, so this is X1, comma Y1, so it would be 1 minus 0.75 divided by 3, which would equal about 0.0833. So W new, yeah, I don't want to put new at the bottom because I got eyes running around down there, so I'm going to put it at the top. So W1 new would be 0.25, which is W1 old, plus 0.0833, which is delta W1. Which would equal, if you did the math here, you get 0.333333, which is 1/3. So we just used 3,1 to get the line that would basically go out here, and it would intersect the green point, 3, 1. So that would be 1/3 x. Okay, so it's better than 0.25. So let's find out what happens when we learn our next point. So let's learn 1, 3. Again, this is x2, y2, and we get O2 is equal to, now I'm going to use my updated W, which is 1/3 times 1, which is 1/3. So my delta W2 would be 3 minus 1/3 divided by 1. In this case would be 8/3. So we just did a little bit on there, and you get W2 new. So W2 new would be my W2 old, which is my 1/3, plus delta W2. So that would be 1/3 plus 8/3, which would be 3. So my new W2, after using these two pieces of data, so I'm going to change colors to orange here, would basically take my point and shoot it right up through my point. So this is 3x. So what's happening? Hopefully you kind of see what's going on here. So what is this process doing? So this process will never get better. Get better at classifying all of the data. And hopefully you can see why. Because what's happening is every single time you put a new data point in, all it does is it just puts a line right over the top of that line or that data point. And so what you're doing is you're I'm gonna put it in quotation marks here. You're forgetting all of the past data. So what do we want to do instead? So instead, use a learning rate. Okay, and let's just go ahead and see what happens when we use some kind of learning rate. In other words, I don't want to jump. And this delta W1 shouldn't be full board all out to that next point. It should use a piece of that data and then some of what you had in the past. So let's let new equal to 0. This will be easy for me to do my calculations with. So 0.5. So it's something a little bit easier for us to work with. So in that case, let's start back with our W1 is equal to 0.25. And then let's learn 3,1 now with the learning rate. So we know that O1 is equal to 0.75 because we've already done that one. And therefore, delta W1 is equal to 1 minus 0.75 divided by 3. And now I'm going to put my learning rate in here, 0.5. Then we get 0.04. And I already have this math worked out, but it would take a calculator for me to do this. So that W1 new would equal to W1 old plus delta W1, which now is 0.25 plus 0.041667, which is 0.291667. All right, so that's now my new W2. So that's W moving forward. And let's learn 1, 3. So O2 now would be equal to 0.291667 times 1. I'm going to just use 0.29. So delta W2, and so I'm using delta 1 as being my first update and delta 2 as being my second update. Later on, we're not going to have the luxury of that. So it's going to have to be delta 1 old, delta 1 new, and then when you learn your new piece of data, you're going to have to use old and new again. So delta W12 is 3, right? Because this would be Y2 and X2. So 3 minus 0.291667 divided by 1, all times my learning rate, which is 0.5. We would get 1.35417. So that my delta new, or my W new, would equal to 0.291667, my old one, plus 1.35417, which in this case would be 1.64583. And as you can see, if W is 1.64, so if we went back to our graph, 1, 2, 3, 1, 2, 3, we know we have a point here and a point here, and then 1.645 would give us a line sort of in the middle here, and it would do a lot better job of. So you can see now what's happening. When you get a learning rate, you don't forget the things that happened in the past. You start using the information, the new information with the stuff from the past. So that's the idea. That's what we wanted to get to. Now I want to connect this to a neural net. So what would this look like if we were going to do it in a neural net? And then maybe talk about some training. The training algorithm sort of changes a little bit based on the fact that we're linking it to a neural net. So we'll call this connect to a neural net. If you're looking at the R notebook that I have on the course website, it actually is a little more advanced than the one that we're doing now. So it goes right to what we're going to talk about at the very end of today's lecture. So I have X1. Well, let me define what X1 is here real quick. So now I have more than one piece of information going in. So now I'm going to have X1, X2, and this is going to be my width, my length, and the target is now going to be either a 0 or a 1. So we'll let 1, 3, I believe is what, was that what our table was earlier? Let's make sure. 3, 1. So let's just have the same data that we had before. So it was 3, 1, and then 1, 3, and then we let 3, 1 be. So it's 3 width. This would be a ladybug here, because it only has 1 width, and this would be a caterpillar. And this one would be a ladybug. So if I'm longer than I am wide, make sure that's what we called it up there. Cat and ladybug. You're killing me. All right, so maybe this didn't make a whole lot of sense. So only okay. I changed it. I changed length and width. Let's do that. Let's just change this bad boy back to width and length. I messed that up again. Yeah. So let's change it to length and width. Length and width. And that will change this. So if I'm 3 long and 1 wide, that is a caterpillar. This is a ladybug. And then I'm going to let that be 0. And I'm going to let this one be 1. So we're going to need that here in a few minutes when we get over to R training this thing. So if that's the case, then let's draw our model. So I got X1 now, and now I got 2 components going into it. This is going to be what's called our input layer, and I have 1 node. So our input layer has 1 node. And then here, let me move this up a little bit, and then what we're going to do is an activation function. In this case, a step activation function. And what's going to pop out is either a 0 or a 1. So 0 equals caterpillar if you sum this thing up and you multiply x of I times wi. Oh, I forgot to put, so this will be w1 and this will be w2. So now I have 2 weights, not just 1 weight anymore. But when I multiply those weights by x, if I get some value that is less than 0, then I want it to be 0. If I get some value that is greater than 0, then I want I want it to be a ladybug. Okay. So let's talk about, well, we could talk about that function here real quick. So what it's doing, I know we're going to have to deal with this again in the future. So the reason why it's it's going to be a 0, 0, 0, 0, 0 up to this point, and it's going to jump up to a 1. So let that be 0, and then it's going to for all other values. So that's the activate. It's called an activation function. And we're going to use a different type of activation function later. But for right now, we're just going to use this little step function. So if I want to classify, if I want to train this network now, and I'm going to hook, again, we're hooking this thing up to a neural net. So training a neural net. Matter of fact, let's don't even call it a neural net yet, because really we're not to a neural net. We're perceptron network. So we want to train a perceptron network. And what we want to do is I want to initialize, so and we'll get to R and we'll do this here in a second. We're going to initialize the weight, actually weights this time. And then we want to, so first initialize, and then we want to iterate this thing. So iterate until convergence. So I'm going to calculate this delta WI. And all that is going to be my learning rate times Y, so my target minus my output. And then instead of dividing by X, we're multiplying. We're going to multiply by X, because I want to, if X is large, then it's contributing a lot to the fact that this thing is in the wrong direction. If X is small, then it's not contributing. If X is 0, it's not contributing anything. So I want to keep doing that. And then I'm going to call this WI new is equal to WI old plus delta WI. So all you're doing is just keep changing W's until you get the same W's for consecutive terms. So once the W's have converged, Y sub I minus O sub I will always give you the same number, and then you'll have no change. This delta WI will be 0. So that's the idea behind it. Let's go to R and see if we can. So let me push R over. Stop sharing. All right. So let's go ahead and start doing some of this in R. So let's define this perceptron function. W, X being my input, W being my weights. And I'm going to set this P sum of X. Basically, you're just doing the dot product between those two vectors. And then we're going to pass out either a 0 or a 1. So if P is greater than 0, then answer equals 1. Else 0, and then return answer. So that should work. Then we want to do this train function. So that is also a function. X, W. I need my target, and I need my learning rate. So those are the things that you need in order to train. I'm going to let O, so this is not a 0, it's an O. So O is equal to perceptron X comma W. Then for each, so for I in 1 through length W, we want to go in and have its delta equal to learning rate times y minus O times xi. Okay, so y minus O for each W, I'm going to change. Yeah, so for each W, I'm going to change it. All right, so Wi is equal to Wi times this delta. I'm sorry, not times, plus. It's got to be plus. That's this delta W. I guess I could have wrote a W there too to make it more clear. That's all we're doing. So we're gonna, and then I want to return back so return our W. W comes in as a vector, X comes in as a vector, Y is just a target, and O is going to be the output based on X and W. And the learning rate is going to be that thing that we talked about where you want to keep track of, or you want to keep some of the old information that you've already used to train. So that's what we're doing. All right, and then maybe learning rate, let's let it equal 0.3. I don't have to do the math on this one, so it's not that difficult. And we'll again arbitrarily just 1 and 1. So we'll let our weight start off at 1 and 1, and then we will set X equal to 1 and 3. What did we say 1 and 3 was? Was that a 1? So we'll let that be 1. So this is a ladybug, 1 length, 3 width, and we said ladybugs for right now are equal to, or should be targeted as 1. All right, so let's go ahead and train it. So W is equal to train, comma W, comma Y, comma learning rate. So check out what this is doing. So X starts off 1, 3. And we know 1, 3 is a ladybug, so we're going to say that's y is equal to 1. And that's how we want to train that. So in that, we also want, we can print it off. So let's go ahead and print. Now I want to say X is equal to, because we got to train both of these. So 1, 3, no, 3, 1, 3, 1. And then it's length of 3, so that's a caterpillar, so that's a 0. W is equal to, so we're going to train this one as well. Train X, comma W, comma Y, comma, and then print W. So we're printing these so that we know when it's converged. So it's going to start off at 1, 1, and it's going to just keep going around until it's trained it. So Control Enter. I didn't like that at all because I haven't done any of this yet. So Control Enter. I want to do this one, Control Enter, and then we're going to have this one so that it just keeps printing off. Oh, I forgot to put the C's here. Sorry. Try it again. So 1, 1. Oh, look at that. So after just a couple of shift enters, you get negative point. So negative 0.8 and then 0.4 as my 2 weights. And let's see what that looks like. So if I had well, let's do the one that we had in the problem, right? So we wanted to know how should we classify if X were 2.5 and 0.8. And perceptron. Perceptron is the model, and we're going to put in X and W. 0. Does that make sense? Is 0, 3, yeah, it is. So it's the one that was closest to 3, 1. So 2, 5, 0.8 does make sense. And we could put a bunch of different values in here to test it, or we could do a picture, right? So hopefully the picture's worth 1,000 words, and we can do that. So let's go ahead and throw in a picture. So in order to do that, we're going to use mesh grid because I'm going to mesh the X's and Y's together. So we got to bring in Procma. Control Enter. X equals, so in length space is a Procma thing. So if you don't have Proxima, you probably, this will give you an error. It'll only take you a second to get Proxima. So y is equal to len space. And there's other ways to do len space besides this, but I'm going to go from 0 to 4 and 0 to 4. So we get x's and y's. We get d is equal to mesh grid x comma y. And then what that returns is two lists, and I'm going to put them in x. So d $x y cap. And these are capital letters. So d $y. And now we have two data frames for x's and y's that are spread throughout 0 and 4 x's and y's. And so now what we're going to do is, so I'm going to create another, so show result and create another function. And I'm going to pass in capital X and Y and my weights. So I need a color list. That's all this is. 0 for black and 1 for white, I believe. M is equal to length of my rows, so all the rows in column 1. N is equal to the length by columns, so all in row 1, all the columns. So that's M and N for us. And we're going to have this image picture of what's going on here. And right now it's just going to be a matrix of zeros. 0, comma, n row equals m, n column equals n. Then we simply want to go through I 1 through m. J through n. Take some of these spaces out. X equals to C of ij. So I'm going into that data frame and grabbing the ij one piece out of from the x value, and then the y matrix, I'm going in and grabbing that one. Then we want to have image I comma j, our perceptron. W. And then eventually we want to return, or we want to do something about, so maybe image, img, and color is equal to that color list that we set up there. Okay. And we could do other things with this, but we'll enter. Then I want to show result x comma y comma the w's that we just created, and see what that would look like for all of these different things. And if you remember, the ones are our white and the zeros are our black. So the question is, did it get it right? And if we go back to what we said was that, let's see, go up here. So 1, 3 was 1. So 1, 3. So the ones that are down here, the down lower are the ones, and the 3 ones are the zeros. And so yeah, that makes a lot of sense for this particular problem. Now, what if I wanted to change this? Would it work? So that, I guess that's a question. If I started, I don't even have to start over my W's. What if I said I want, instead of this being, so again, what we intend to do now is flip this thing. I want the blacks up top and the whites on bottom. So if I change this to 0, and change this to 1, would we be able to do this? The question. Full enter. Control. Keep doing this until you get the same number, and we just did. And let's see if that works now. So we get a 1 now instead of a 0. So yes, it's the one that's closest to that one again. And let's see what it looks like. See the result. Okay. So now we get the blacks up top and the whites down low. So you can see what's happening in the neural net, if you will. Or, I'm sorry, in the neural perceptron network. What this thing is doing is it's changing your weights so that the target is met. And it's remembering some of them because we're using the learning rate. The last thing that I want to do before we take off for this particular video, so I'm going to stop sharing this. We're going to tab back over to our OneNote. And I'm just going to introduce a new problem. So, because we do have problems. We have a problem with this one right now. We haven't introduced this thing called a bias term. And there's a reason why we need a bias term. But let's figure out why. So first, one of the things that folks try to do, and this part is in the R notebook that's in your it's on the course website. So one of the things that people try to do is use these perceptron networks to come up with an AND truth table and an OR truth table. And if we just had two numbers, x1 and x2, so 0, 0, and then the output of that would be x1 and x2. So Boolean logic leads us down the road for these truth tables, and you would get 0, 1, 1, 0, 1, 1. So we'd get 0, 0, 0, and 1. And what does that look like graphically? So graphically, if I tried to use the current perceptron network that we have up there, it wouldn't work, and here's why. So I would have, let me take that one away. I would have a 1 and a 1, and if I let green be 1s, in this case I only have 1. So I have a green there, and I have 0 here, so I'm letting this be 0, 0, 0, and I'm letting the green be the 1. And then there's the 0 here. There's no way for me to draw a line that started at 0, 0 and would separate this data. I could draw a line this way and separate the data. Matter of fact, there's lots of lines that I could draw that way to separate the reds from the greens. But the problem is right now, the way we got it set up is there is no way to do that because all of our lines are starting from 0, 0. So there's no way for me to do that. And if you looked at the OR table, it would be the same way. So if you had x1, x2, x1 or x2, it would be something very similar where we wouldn't be able to do it without this new term. And if you just remember from your high school days, that term would be what's called a y-intercept. And in neural net or perceptron terminology, it's called bias. So there's a bias term that we need to be worried about. And the way that we're going to do that is we're going to add it on, we're going to call it x0, and it's always equal to 1 times, so it's always there, and it's a 1 that's always in here, and it's another number. And so basically what it allows you to do is have a weight that is your y-intercept. So you can kind of see the math behind it in order to make that work. So that's what we're going to be talking about in the next video. So I'm going to start with these truth tables, and we will go to R, and you can again look in the notebook that I've given you, and you can see some of the data that's in there and how that thing's working, and how the training. So the training is going to be exactly the same, except so we're going to have another term around there, and we'll see what happens. Okay, that's all I got for this particular